Hi students, welcome to the lecture Boolean Theorems and Logic Operations. Coming to the Boolean Theorems and Logic Operations. So Boolean Theorem, it is nothing but as in our digital subject we are implementing any type of logic by using some functionality. So that functions we are generally calling as, we are representing as Boolean functions. Okay, for knowing the relationships, for identifying the behavior of these Boolean functions, we have to see the first basic one is Boolean theorems. So coming to that, the second part of this first unit is consisting of this number of topics. So the first topic is logic operations. This operation, the logic gates operations, we have seen in the lecture level. Now we will see the remaining topics other than logic gates. The remaining operations we will see in this remaining part of this first unit. So coming to that, the first topic in this class, we are going to discuss about Boolean theorems and principles of complementation, duality and De Morgan theorems. Next, coming to that, standard SOP and POS forms, where SOP is a sum of products and product of sums. So we will see some standard and canonical SOP and POS forms. Next, NAND, NAND and NOR realizations. In any type of circuit, in the digital side, any type of circuit we can implement by using NAND gates or NOR gates. How those gates we will represent by using these type of NAND and NOR gates that we will see in this concept. We will realize different types of Boolean functions by using this NAND and NOR gates. Next, realization of three-level logic circuits. So we will see different types of three-level logic circuits. So coming to take any Boolean function, here we have only two levels. The first level is AND gate, second level is OR gate. But other than this, we will see different types of levels representing logic gates. Okay, first we will see how the logic gates are representing generally, then we will see the three-level logic gates. Next, this is the very important topic and this is added newly in our R19 syllabus. That is, study of the pin diagram and obtain truth table for the following relevant ICs, that is IC 7400, 7402, 7404, 7408, 7432, 7486. So this is the new topic added in this R19 curriculum. In the previous curriculum, this topic is not added. So it is nothing but as whatever the NAND gates, NOR gates we have learned, that we will see based on the industry point of view. So actually this type of ICs we are using in commercially in our electronic God gates. That IC specifications we have to see. The same AND gate principle is there in this IC, but how that is framed in that particular IC, that we will see. So these are the contents of the second part of the first unit. So coming to that, so the first we will see Boolean postulates and theorems. So some of the Boolean postulates and theorems we have to see now. Okay. So coming to here, the postulates are the universal facts given by the digital technology subject, and coming to the theorems, we are assuming some of the theorems and we have to prove those theorems. So these are the facts, and these are by using these facts we have to prove theorems. Okay, so postulates and theorems. So coming to here, the first postulate 2a. So coming to this postulate, x plus 0 is equal to x. X plus 0 is equal to x. For example, in the place of x you keep 1. 1 plus 0, 1. If you keep x in the place of x, 0. So that is equal as 0 plus 0, 0. So whatever the x value is here, the x value is reflecting as answer. X plus 0 is equal to x. Here the x is nothing but as a binary signal. X is nothing but as a binary signal. X, y, z, a, b, c, whatever the variable you want to represent, you can represent. So this is a variable. This is a binary signal. The binary signal has only two forms, 0 and 1. So this is either 0 or 1. In the place of x, if you put 0, 0 plus 0 is equal to 0. In the place of x, if you put 1, 1 plus 0 is equal to 1. So the x value is representing as x. So this is a universal fact. So coming to that, the second postulate we have B condition, B postulate also. In the postulate 2 we have A and B. So coming to B, x into 1 is equal to x. So 1 into 1 is equal to 1, 1 into 0 into 1, that is equal to 0. If x is equal to 0, the product of this one is equal to 0. If x is equal to 1, the product of this one is equal to 1. So finally, the x only reading as output. So in the same way, postulate 5, x plus x bar is equal to 1. If x is equal to 0, what is the x bar? If x is equal to 0, x bar is equal to what? X bar is equal to 0. Oh, sorry, x is equal to 0, x bar is equal to 1. If x is equal to 0, then x bar is equal to 1. X bar we can represent in this fashion. Okay, you can represent x bar in this way. Otherwise, you can represent x bar like this. Okay, so in any way you can represent the x bar value. Okay, x plus x bar is equal to 1. So if x is equal to 0, x bar is equal to 1. If x is equal to 1, x bar is equal to 0. 0 plus 1 is equal to 1. 1 plus 0 is equal to 1. So whatever it may be. So x value may be anything. If x plus x bar is there, then automatically the value is equal to 1. Next. Postulate 5b. X into x is equal to 0. 0 into 0, 0. 1 into 1. That is equal to 1. So in the place of x, if you put 0 or 1, so whatever may be, that is that leads to 0. Right? A small modification here we have. So that is nothing but as x into x bar. Here x plus x bar. Here we have to say x into x bar. The same operation with there here plus with the dot operation. X plus x bar is equal to 1. X into x bar is equal to 0. Okay, right. Theorem 1. So theorem 1 you have to prove by using this postulates. Here theorem 1. X plus x is equal to x. X plus x is equal to x. X into x is equal to x. We have to prove this one. Next theorem 2. X plus 1 is equal to 1 and x dot 0 is equal to 0. X dot 0 is equal to 0. That is also we have to prove. Next theorem 3a. X bar whole bar is equal to x. Here theorem A is representing x bar whole bar. For example, x is equal to x is equal to 0, then x bar is equal to 1, right? X bar whole bar. So the complement of this one is equal to 0. The complement of this one is equal to 0. So x double bar is equal to 0. That is we are representing here. X double bar is equal to x. X value is 0. So here x double bar is equal to x. So the 0 we got the same 0 here. So for that reason x double bar is equal to x. So that is also one universal fact. Next, postulate 3. X plus y is equal to y plus x. That is we know from the childhood. Xy is equal to yx. We can write anyway. Next theorem 4. X plus of y plus z is equal to x plus y plus z. Next, x of yz is equal to xy of z. Next, that is postulate for. That is theorem 4. Next, postulate 4. X of y plus z is equal to xy plus xz. This is nothing but as distributive law. This is called distributive law. X plus yz is equal to x plus y into x plus z. Next, theorem 5. X plus y is equal to xy. Xy is equal to x plus y. Next, coming to theorem 5, x plus y whole bar is equal to x bar dot y bar. So here the complement operation for this, the complement operation x plus y whole bar. So when you are applied this complement, so this complement, you are distributing the complement to each and every one. So x bar plus bar y bar. So coming to x is changed to x bar, y is changed to y bar. Now the plus bar is changed to dot. So this is the x dot y. So x bar dot y bar. You can represent x bar dot y bar like that. Otherwise you can represent x bar dot y bar in this way. Okay, so this is the property of theorem 5. This is the property of theorem 5. X plus y whole bar is equal to x bar dot y bar. So this is the function. So in the same way, xy whole bar is equal to x bar plus y bar. x bar plus y bar. That is the theorem 5. That is that proof also we will see in the next slides. Theorem 6, x plus xy is equal to x, x of x plus y is equal to x. So this is one more property. This is also we have to prove for the theorem 6. So these are the theorems and postulates here we have. We will prove these theorems and postulates. Next. So coming to theorem 1a. So coming to theorem 1a, see here, this is theorem 1a. So theorem 1a is equal to x plus x is equal to x. X plus x is equal to x. That is we have to prove. So see here, this is the theorem 1a. Here I have written. So the same slide, whatever the slide is here available, that's here. Here I have kept here. So x plus x is equal to x. Right. So here, first take LHS, that is x plus x. So here I have taken LHS x plus x. X plus x, I am writing like this. X plus x, I am writing x plus x into 1. Okay, into 1. So check this one. So consider x plus x is equal to some y. Y into 1. Is there any modification? Y into 1, that is equal to y. So we know the property from postulate to b. So here, this is the postulate and this is the postulate to b. X into 1 is equal to x. X into 1, x is equal to x. So I am considering this term as some variable. That is, I am representing there x into 1. So that variable into 1, same the variable we will get from the postulate b. So postulate is nothing but as fact, and theorem we have to prove. Okay, the theorem 1a we have to prove by using postulate. So x into 1 is equal to x. This property we brought from 2b. Okay, that is the first step. Next, coming to the second step. So you multiply the in the place of 1. In the place of 1, I am writing x plus x bar is equal to 1. X plus x bar is equal to 1. So in the place of 1, I am writing x plus x bar. In the place of 1, I am writing x plus x bar. Next, coming to here, multiply this, you have to multiply this one, x into this 2 and x into with this 2. You have to multiply this one. So after multiplying, you will get x plus xx bar. X plus xx bar from the 4b, that is postulate 4b. So this is the property. So this is the property check. This is the property of 4b. So what there in the 4b? What is there from the 4b? Not 4b. Sorry. Postulate 4b. Here we have taken theorem. It's not correct. So this is the postulate 4 and this is the 4b. So what is this expression? X plus yz is equal to x plus y into x plus z. So I am writing separately here, that is x plus yz. This is I am writing x plus y into x plus z. So this is the distributive property. This is the distributive property. You have to multiply x with this 2 and you have to multiply y with this 2. So x into x, the first term, plus x into z plus next y into x, that is xy, y into z, next that is yz. Okay, so this is the property. So coming to here, x into x, that is nothing but as x, plus next xz plus xy plus yz. Okay, so this is the formula we got. X plus xz, common x value, then 1 plus z plus xy plus yz. So 1 plus z, 1 plus anything, what happened? In the place of z you keep 0. 1 plus 0, value 1. In the place of z you keep 1. 1 plus 1 is equal to 1. So 1 plus z is equal to 1. X of 1 plus xy plus yz. Next, here from this 2 you have to write down, from this 2, x plus xy plus yz. From this 2 you have to take common x value. If you common x, then 1 plus y is the remaining one and yz. Next, 1 plus y, if in the place of y you keep 0, 1 plus 0, 1. In the place of y you keep 1, 1 plus 1 is equal to 1. Here plus is nothing but as OR gate logic. Plus is nothing but as OR gate logic. So remember that one. 1 plus 1 is equal to 1. So finally here we have x plus y z. So this is the property, distributive property. So that is the distributive property, that is 4b. From the 4b I am writing the that. So see here, this is considered some x plus y and this is considered some x plus z. In the place of y also here we have x. See here, I am writing here again here x plus y, x plus z. Okay, based on this distributive property, right? Based on this distributive property. Okay, here x plus x and x plus x bar is there. X plus x and x plus x bar is there. Now simplify this one and write down the equation. So in the place of y we have x, we have written the same thing. In the place of z we have x bar, that is we have written here. Okay, so this is the property we have written from the 4b. From the 4b we have written the condition like this. Excuse me. Now see here, coming to the next step, again simplification we have to do here. So coming to the simplification, x into x bar is equal to what? So now tell me the value of x into x bar is equal to what? You can see from the postulates. So with the help of the postulates, what is the value of that one? X into x bar is equal to what? See here, x into x bar. Here we have postulate 5b. So from the postulate 5b, x into x bar is equal to 0. So x into x bar is equal to 0. Now you can write x plus 0. X plus 0 from the what? 5b, right? So that is our next step. So x plus 0. X plus 0, that is from equation 5b. Next coming to here, x plus 0 is equal to x from 2a. In the place of 2a check here, x plus 0 is equal to x. X plus 0 is equal to x, that is from 2a. So see here, this left side, coming to this right side. So these are our postulates. You have to take all these from the postulates. So postulates are the universal facts. With the help of universal facts, you have to prove theorem 1a. So coming to theorem 1a, x plus x is equal to x. So x plus x is equal to, I am writing x plus x into 1. So there is no change. In generally, we can know that if you multiplying with 1, it's nothing happen. So but we have to take that from the universal fact, that is from postulate 2b. Next coming to that, x plus x into x plus x bar is equal, we have written in the place of 1 x plus x bar. In the place of 1 I have written x plus x bar from the which postulate? X plus x bar is equal to 1. So that is a postulate from 5a. So from postulate 5a I have written 1 as x plus x bar. Now I am multiplying these two by using distributive property. So based on distributive property, in the red color box I have represented x plus yz is equal to x plus y into x plus z. Then only you have to see. Okay. So then this one we can write as x plus yz. In the place of y we have x. In the place of z we have x bar. X plus x into x bar. Next, x into x bar is equal to 0 from the postulate 5b. From the postulate 5b, x into x bar is equal to 0. That is, we have written x plus 0 is equal to x. So finally, here this is nothing but as RHS. This is nothing but as RHS. So we are proving x plus x is equal to x. This is very simple operation. This is the theorem 1a. Next, coming to the theorem 1b. In the same way, in the same way here, in the same way, theorem 1b, x into x is equal to x. So this is the theorem 1b. So we have to prove this one, right? First take LHS, x into x. So here I have written x into x. So by using postulate 2a, I am writing x into x plus 0. So here dot is there, that dot I am not representing. Why? Because dot we cannot, there is nothing else, it is representing the AND operation, it is nothing else product operation, that is I am represented here, x into x like this way, like in this way. So x into x plus 0, okay. So so if you are adding some 0, nothing happened to the function. So for that reason I have added plus 0 from the postulate 2a fact. Next, coming to that, in the place of 0 I am writing x into x bar. In the place of 0 I am writing x into x bar, x into x bar. That is from postulate 5b. So what is postulate 5b? From the postulate 5b, x into x bar is equal to 0. X into x bar is equal to 0. From the postulate 5b, I have written the function like this. Next, coming to here. So, in these two words, in these two products, I have taken common as x. Then the remaining x plus x bar I have represented here. X plus x bar I have represented here. Right, x plus x bar is the remaining value. So x plus x bar is equal to what? X plus x bar is equal to 1 from postulate 5a. So by using from postulate 5a, x plus x bar is equal to 1. I have represented x into 1, x into 1. Next, coming to that, x into 1 is equal to x from 2b. So what is the postulate 2b? X into 1 is equal to x. So x into 1 is equal to x. So this is the theorem 1b. This is the theorem 1b. So it's very simple thing. X into x is equal to x we have to prove. X into x is equal to x into x plus 0. I have added plus 0. Next, in the place of 0, I have kept x into x bar by using postulate 5b. So x into x bar. In these two terms, I have taken common as x. Then the remaining value x plus x bar is there. So x plus x bar is equal to 1 from the postulate 5a. That postulate 5a I have represented here x into 1. And the final value is equal to x. Final value is equal to x. So this is the RHS value. This is the RHS value. So LH is equal to RHS. So this is the final value. X dot x is equal to x. Okay. Right. Next, postulate 2a. X plus 1 is equal to x. X plus 1 is equal to x. X plus 1, I am writing here 1 into x plus 1. So 1 into, nothing will happen from postulate 2b. I have taken 1. So in the place of 1, I am writing x plus x bar into x plus 1. In the place of 1, I am writing x plus x bar. In the place of 1, I am writing x plus x bar. Now, this seems to be like as a distributive property. Now multiply this one. X plus x bar, x plus 1. That is x plus y into x plus z. In the place of y, we have x bar. So see here. In the place of y, here we have. So this is the property. X plus yz is equal to x plus y into x plus z. In the place of y, we have x bar. In the place of z, we have 1. So now the next step is x plus yz. X plus yz means x plus, in the place of y we have x bar, and in the place of z we have 1. That is nothing but as x plus x bar into 1. X plus x bar into 1. X plus x bar into 1. Next, coming to here, x bar into 1. X bar into 1. What is the value of x bar into 1? That is nothing but as x into 1 is equal to x. That is I am represented x bar. Okay, x bar into 1. That I am writing as x bar. Now x plus x bar is equal to what? X plus x bar is equal to what? So see here, x plus x bar is equal to 1. X plus x bar is equal to 1 from the postulate 5a. From the postulate 5a, I have written 1. So x plus 1 is equal to 1. X plus 1 is equal to 1. So this is the postulate 2a. So this is the RHS. Now LH is equal to RHS. Next, 2b, you have to practice. So three theorems we have solved. That is 1a, 1b, 2a. So now 2b you have to make as a practice. Next, theorem 6a. 6a is equal to 6a theorem is x plus xy is equal to x. X plus xy is equal to x. Now we have to prove this theorem. So coming to here, LHS, that is x plus xy. Write down x plus xy. X plus xy I have written here. So in the place of x, I am writing x into 1. In the place of x, I am writing x into 1. X into 1. Anything into 1, anything. Okay, y into 1, y. Z into 1, z. So we will get the same variable x into 1. So that is from postulate 2b. See here, from postulate 2b, x into 1 is equal to x. So that is I have written same as this. Next, so in this 2, I have taken common as x. Now I have taken x is common. So after taking this one, so here 1 plus y is the remaining value. So here we have 1 plus y. So coming to here, 1 plus y. So here x plus 1. So see here theorem 2a, x plus 1 is equal to 1. From theorem 2a, we have x plus 1 is equal to 1. Okay, so 1 plus y is equal to what? 1 plus y is equal to 1. Why? Because in the place of y you put 0. Y may be 0 or 1, we don't know, but that is a variable. If it may be variable, the y value may be 0 or 1. In the place of if you put the value is equal to 0, 1 plus 0, 1. In the place of 1, if you in the place of y, if you put 1, 1 plus 1 is equal to 1. So here the final value 1 plus y is equal to 1. Okay, from postulate 3a, sorry, from postulate from theorem. From postulate 3a, x plus y is equal to y plus x. See here, x plus y is equal to y plus x. 1 plus y I am writing as y plus 1. Y plus 1. So 1 plus y I am representing as y plus 1. Whatever it may be is not a big problem. Why? Because based on commutative law, we can represent the function like this. Next, y plus 1 in the place of y plus 1. So see here. So this one. Theorem 2a, from theorem 2a, x plus 1 is equal to x. That is, we are writing here y plus 1 is equal to 1. X into 1 is equal to x. From the postulate 2b, from the postulate 2b, we have used almost all the postulates. We have not taken any theorem help. We have taken all the postulate help and we have proved that x plus xy is equal to x. X plus xy is equal to x. That is equal to RHS. So LH is equal to RHS. Okay. Next, so the theorem 6a we can prove by using another method. So x is nothing but as a binary signal, y is nothing but as a binary signal. In our digital subject or in our STLD subject, wherever the variable if you have taken, we can represent by using x, y or z or maybe L, M, N or A, B, C, whatever it may be. All the variables, it has only two forms, either 0 or 1. The x signal we can represent either 0 or 1. So any binary signal we can represent by using zeros and 1s. Okay, so coming to here, so here we have x, y two input signals, the x signal and y signal. So coming to the maximum possible combinations for these two signals. Here we have two input signals. Okay, so the maximum possible combinations we can get by using the formula of 2 power n, where n is the nothing but as number of input signals. Where n is the number of input signals. Here we have two input signals. Here we have two input signals. That is nothing but as x and y. So in the place of n, you have to keep 2. So 2 power 2. So the maximum possible combinations are 4. So the possible combinations we have to see here. So the x value may be 0. The y value may be 0. The x value may be 1. The y value may be 1. Maybe this one 0, this one 1, this may be 1, this may be 0. So all the possible combinations we have represented here. 0, 0, 0, 1, 1, 0, 1, 1. By using these two input signals, these are the maximum possible combinations. Other than this, we don't have any possible combinations. Next, in this equation at the LHS side, we have XY operation. X operation is there, XY operation is there. So XY operation, XY is written as X and Y. X and logic and Y. Okay, so X and Y combination is here. So X into Y. So based on aggregate functionality, if both inputs are high, then only the output is high. Otherwise, in the remaining all condition, the output is low. High is nothing but as logic 1 and low is nothing but as logic 0. Okay, that high operation we are representing 1. If both inputs are high, then the output is equal to high. If both inputs are 1, output is equal to 1. If any one of the input signal is low, that is 0, output automatically 0. So this is the AND gate operation. Now next, coming to here from the our LHS side, x plus xy. Okay, see here, x plus xy. So this is the x, this is the x, and this is the xy. Okay, so in between these two, what you have to do? You have to do the OR gate operation. What is the OR gate operation? What is the OR gate operation? If any one of the input signal is 1 or high, either 1, we can call high as nothing but as logic 1. If any one of the input signal is 1, automatically the output is 1. Otherwise, in the remaining cases, output is equal to 0. So see here the first case. Here x value 0 and xy value 0. So both inputs are 0. 0 plus 0, 0 with R, 0, 0. Okay, next 0 and 1, 0. In this case also, two inputs are zeros. So here again I have written 0. Now in the third case, see the third case. In the third case, here one input is 1, another input is 0. That is x value. So here x value is 1. Sorry, it's not 0. It's 1. And xy value is 0. 1 plus 0. Okay, based on the OR gate logic, if any one of the input is equal to 1, then automatically output is equal to 1. So here we have written 1. So here x value 1 and xy value 1. X value 1 and xy value 1. Here 1, this is also 1. 1 plus 1 is equal to 1. If any one of the input is equal to 1, automatically the output is 1. Here both inputs are 1, so output is 1. Okay, so this is the x plus xy operation. X plus xy operation. Next. What is the RHS value x? What is the x value? 0011. 0011. Right. Now you have to prove LHS is equal to RHS. So LHS value x plus xy, that is I represented with the green color box representation. Here x value I have also represented with green color box. So see this green color boxes, x plus xy value and x value, both are same or not? Both are same or not? So in the last slide, we have taken the help of postulates. By taking the postulate, we have proved that LHS is equal to RHS for the same 6A theorem. In this example, in this slide, we are proving that the maximum possible combinations zeros and ones were represented here. From these zeros and ones inputs, we have represented x plus xy operation and x operation. Here LHS is equal to RHS. The same x value, whatever it may be there here or from the left side of the board, that is I have represented the right side of the board also, same x value. So x plus xy is equal to x, both are same. LHS is equal to RHS. So here x is like this 0011. The same 0011 I have kept. I am not changed any x value. So this is the theorem 6A proof. In the same way, the 6B, x of x plus y is equal to x. Now prove this one. Start proving. Pause the video and stop. Right. So coming to here, so I think you have solved. So see here, x of x plus y is equal to x. Here we have one term x plus y, another term x. So xy values I have written here. X plus y also I have written there. If any one of the input signal x plus y is equal to 1. So in this first case, both inputs are 0. The output is equal to 0. Here y input is 1. Here x input is 1. Here both inputs are 1. Okay. So any one of the input is equal to 1, automatically the output is 1. So x plus y is equal to 0, 111. Now what is operation? X into x plus y. You have to multiply, you have to do the AND operation in between x and x plus y. So this one and this one you have to multiply, that is product operation or AND gate operation. Why? Because AND gate operation, product operation, both are same. There is no change at the output. Now x plus xy, this one into this one, 0 into 0, 0, 0 into 1, 0, 1 into 1, 1, 1 into 1, 1. So that is the x of x plus y. So this is the LHS value. Next, RHS value. RHS value, x value, whatever the value here we have taken, the same value you have to represent there. So 0011, 0011. That is the RHS value. That is the RHS value. Okay. So LHS is equal to RHS. So there is no change. in the previous slide, so see here, in the previous slide, x plus xy and x both are same. In this present slide, x of x plus y and x both are same. There is no change. Xy, there is no change in the previous slide to present slide. This one and these two green color boxes also, there is no change in this. There is only change here x plus y. In the place of x plus y only, here we have change. Okay. So this is the Boolean theorems. Next, coming to the De Morgan laws. Here we have two De Morgan laws. The first one, a plus b whole bar is equal to a bar dot b bar. A plus b whole bar is equal to a bar dot b bar. So this is the first property. Next, second property, a dot b whole bar is equal to a bar plus b bar. A bar plus b bar. So as per from this De Morgan's law, the concept is a plus b whole bar I am representing in this way. So this is correct and this is also correct. You can represent by using any type of method. I don't have any typical bar concepts in the PowerPoint and board. So for that reason, I represented there like this with apostrophe s symbol. That is also complement operation. So this is also complement operation. So this is whole complement. Now apply to individual complement. So this complement you have to apply for A for in between the plus operation and B operation. That is A bar, plus bar, B bar. A bar we can't do anything, so write A bar, and B bar also you have to write. So plus operation bar, the complement operation of plus is shifted to product operation. So this is the product operation, A bar dot B bar. So if you make the complement for the OR gate, it will represent AND gate. Otherwise, AND gate, if you are applying any complement, then you will get OR gate. So AND gate complement is OR gate complement is AND. So 0 is changes to 1, 1 is changes to 0, plus is changed to 0, 0 is changed to plus. That is AND is changes to OR and OR is changes to AND. So coming here, 1 is changes to 0, 0 is changes to 1 and plus bar is changes to dot bar changes to plus. That is AND gate is changes to OR gate changes to AND gate. Okay, so these are the rules and regulations for the De Morgan's law. So coming to the proof of the De Morgan's law. So the first law, x plus y whole bar is equal to x bar dot y bar. So the dot, there is no need of representing separately. The plus we have to represent, but the dot there is no need of representing. The product value there is no need of representing. So you see here, first LHS. What is LHS? X plus y whole bar. So x value, y value, these two are the maximum possible combinations of the inputs. Next, x plus y, if any one of the input is equal to 1, automatically the output is equal to 1, 0, 1, 1, 1, x plus y. So complement x plus y whole bar, x plus y whole bar. So the complement of this one, so whatever the output you got, you reverse the values. Okay, so x plus y whole bar, bar representing it's not. So 0 not, then 0 bar is equal to 1, 1 bar is equal to 0, 1 bar is equal to 0, 1 bar is equal to 0. So this is the LHS value. So that is the LHS value. Now take down the RHS value. So coming to RHS, x bar, y bar. Here we have x bar operation, y bar operation, then x bar into y bar operation. So that is the right side value. X bar, y bar. So these are the xy. These are the xy. Now I have to write down x bar, y bar. Here 0, 0, 0, 1, 1, 0, 1, 1 is there. Now reverse values. So 1, 1. So see here 1, 1. Next 0, 1, 0, 1 changes to 1, 0, 1, 0. 1, 0 changes to 0, 1, 0, 1. Next 1, 1 changes to 0, 0. This is the 0, 0. So x bar, y bar we got here. Next x bar into y bar, x bar and y bar. So that is product operation. So if both inputs are 1, then only output is equal to 1. Sorry, output is equal to 1. If the both inputs, if any one of the input is 0, for the AND gate, the output is equal to 0. So see here in the first combination, both inputs are 1. So output is equal to 1. If any one of the input is equal to 0, in these three conditions, the second input value is 0. Any one of the input is equal to 0. This is 0, this is 0, here this is 0. So automatically output is equal to 0 for the AND gate operation. So this is the RHS. See here, so this is the final value. This is the LHS value, this is the RHS value. Check that both are same or not. Both are same or not? Both are same. So LHS is equal to RHS. So we have proved the De Morgan's first law. We have proved the De Morgan's first law. Okay. Next, coming to the second law. In the same way, you have to do this operation also. X dot y whole bar is equal to x bar plus y bar. X dot y whole bar is equal to x bar plus y bar. So you have to prove this one, right? So first take x and y, then left side we have x dot y and whole bar, x dot y and x dot y whole bar. So you have to prove this one. If any one of the input is equal to 0, then output is equal to 0 for the AND gate. If both inputs are 1, output is equal to 1. So this is the AND gate operation. Here, reverse of the AND gate. 0 changes to 1, 0 changes to 1, 0 changes to 1, 1 changes to 0. Okay, next. Here, x bar plus y bar. Right side we have x bar plus y bar. First find the x bar, next find the y bar, next find the x bar plus y bar. So x bar, y bar. So from the xy we have to write down x bar, y bar. 0, 0 changes to 1, 1. 0, 1 changes to 1, 0. 1, 0 changes to 0, 1. 1, 1 changes to 0, 0. So these are the x bar, y bar values. So you have to use OR operation for these two. 1 plus 1, 1. We know that OR gate operation, if any one of the input is equal to 1, if any one of the input is equal to 1, automatically output 1. 1 plus 1 is equal to 1. 1 plus 0 is equal to 1. 0 plus 1 is equal to 1. 0 plus 0 is equal to 0. Here both inputs are 0, so the output is equal to 0. So this is RHS. So check these two. X plus y whole bar. So see here, x dot y whole bar and x bar plus y bar, both are same or not. So LHS is equal to RHS. Okay. So this is the second law of De Morgan's theorem. Second law of De Morgan's theorem. In the next video, we will see Boolean functions.